I want to talk about an operation that you can perform on square matrices, so matrices that have as many rows as columns, called the determinant. So what we're going to do here only works for square matrices, and you'll see why when you see the formula. What it does is it turns a square matrix into a single number that kind of measures something about the matrix, and we'll talk about what it is that it measures. And it turns out that determinants of larger size matrices are found from determinants of small portions, small square matrices within the larger matrix. So you can actually start by defining the determinant of a 1 by 1 matrix. For example, the determinant of the matrix -5 is, so this is a matrix with a single entry, this DET stands for take the determinant of, and the determinant of -5 is just -5. The determinant of this 1 by 1 matrix, it's a very small, almost silly matrix, but it's 1 by 1. Its determinant is 3. The determinant of any 1 by 1 matrix is just the entry in that 1 by 1 matrix. So then how do we use that to get the determinant of a 2 by 2 matrix? Well, here are a couple of examples of doing that. In any matrix, you can imagine that there's a checkerboard underneath the matrix. It's always plus in the upper left-hand corner, and then since it's a checkerboard, every other time, whether you move over or down, it just changes the sign. So there's this underlying checkerboard. To find the determinant of a matrix, you pick one row or column, it doesn't matter which one, and you expand along that row or column. So I've just picked the first row that contains 2 and 3. The 2 is in the plus position, and the 3 is in the minus position. So whatever this number is, I'm going to leave its sign alone. Think about it as multiplying it by +1. Whatever this number's sign is, I'm going to flip its sign by multiplying it by -1, since it's in a negative position when you compare to the checkerboard. Okay, so we have 2 times the determinant of what's left when you cross out the row and column that the 2 is in. So times the determinant of 5 plus 3, but the 3 is in a negative position, so I change its sign, so -3 times the determinant of what's left when you cross out the row and column that the 3 is in. Well, if you do that, you have this little 1 by 1 determinant 4. Right? So see how I've taken the determinant of a 2 by 2 and I've defined it in terms of the determinants of 2 submatrices, right, together with these numbers which are called the cofactors. So we have 2 times 5 minus 3 times 4. That's 10 minus 12. The determinant is -2. Now, it doesn't matter which row or column you expand along, so you could do this another way. Let's go back to that same matrix, 2, 3, 4, 5. Let's expand along this column. Notice when you look back at the checkerboard, the 3 is in a negative position and the 5 is in a positive position. So we have -3 times the determinant of what you get when you cross out the row and column that that 3 is in. So that's left with the determinant of 4. And then you have 5 times the determinant of what's left when you cross out the column and the row that the 5 is in, right? So the 1 by 1 matrix that's left, this submatrix or minor, is 2. So we have -3 times 4 plus 5 times 2, which is -12, plus 10, which is -2. See, the answer is the same. It doesn't matter. You could check and see if you expand along this first column or expand along that bottom row. You check that the answer is always going to be -2, which is kind of interesting. In fact, we don't really bother to draw the checkerboard when it's a 2 by 2 because we can see that what always happens is you take the product of this diagonal that's down to the right and subtract the product of the diagonal down to the left. Right? So fast way of 2 by 2 is pretty quick. We can see the pattern's always going to create product down to the right minus the product down to the left. So we have 10 minus 12, that's -2. Let's just use the quick formula to find the determinant of this matrix. See, the determinant of this matrix, product down to the right, would be 4 times 7 minus the product down to the right, which is -2 times 4. 4 times 7 is 28, and this is minus negative 8. So we have 28 plus 8 equals 36. There's the determinant. So, we said this determinant measures something. Well, depending on the size of the matrix, the determinant measures different things. If it's a 1 by 1 matrix, one number defines a length. So the determinant gives you a length of something, although it's pretty trivial, right? If it's a 2 by 2 matrix, it turns out that the determinant measures the area of a particular parallelogram. You could think of each column in the matrix as giving directions where to go from the origin or from some starting point. Like this column 4, 4, we could think of that as saying go over 4 and up 4. Okay, so this creates an arrow, which we call a vector. This other column also defines a vector. It says go back 2 and up 7. So go back 2, 4, 5, 6, 7, and up 7. This creates a vector as well. Now, if I were to take a copy of this second vector and move it over and put it on the head, move it over and put it on the head of that first vector, and then if I take a copy of this first vector and move it over here, I get a parallelogram. It's a parallelogram because this segment is parallel to that one, and this one's parallel to that one. So I get a parallelogram. Sorry, my picture doesn't look too much like a parallelogram. But what the determinant is telling us is that the parallelogram created by these two vectors or arrows actually has an area that is 36. Now sometimes the determinant turns out to be negative. If you were to draw the parallelogram created by these two, you would find that the area is just the absolute value of this, which is 2. So you make a little parallelogram. In this first case, we're talking about a parallelogram where you go over 2 and up 4. Okay, and the other one is you go over 3 and up 5. Okay. This is creating a much skinnier parallelogram. And the determinant being negative 2 is just telling us that the area of that parallelogram is 2. So it measures, for a 2 by 2 matrix, the determinant gives the area up to a plus or minus sign, right? It might be negative. We might call it a signed area, so that, since it has a different sign. If you put the two arrows into the matrix in reversed order, it just changes the sign. So see, I switched the two columns. Now I have 3, 5 first, and now 2, 4. 3 times 4 is 12, minus 2 times 5 is 10. Now I get the positive sign. So this is a property of determinants, that if you switch any two rows or switch any two columns, that the determinant will just change sign. Okay, let's see. Now let's figure out how to do it for a 3 by 3 determinant. Here's a 3 by 3 determinant. Again, we can go back to the checkerboard pattern. It's so easy to do 2 by 2 matrices that we'll just reduce the determinant of a 3 by 3 into a bunch of determinants of 2 by 2s. So let's see, we just have to pick a row or column to expand along. It doesn't matter which one, we'll just use the appropriate checkerboard pattern for the one that we choose. It's a good idea to choose a row or column that has a lot of zeros in it, because that will save you some computational time. So I'm going to just use this first column since that has a 0 in it. Remember, 3 is in a plus position because it's in the upper left. That's always plus. And then this checkerboard pattern says that this is in a negative 1, and that's in a plus position. So if we look at the 3, I'll leave its sign alone since it's in the plus position on the checkerboard. If you cross out the row and the column that the 3 is in, you have left this matrix 4, 5, 2, 1. Okay, and then you have negative 1. It's 1, but 1 is in the negative position, so I flip its sign. So negative 1 times the determinant of the 2 by 2 submatrix that you get when you cross out the row and the column that the 1 is in. If you do that, you get negative 1, 2, and 2, 1. So if we compute this, we have 3 times, let's see, what's this? The product down to the right minus the product down to the left would give me 4 minus 10. And we have negative 1 times the product down to the right would give me negative 1 minus the product down to the left would give me 2 times 2, that's 4. So we have 3 times negative 6 minus 1 times negative 5. So negative 18 plus 5 is negative 13. A 1 by 1 determinant measures length, a 2 by 2 measures area, and a 3 by 3 measures volume. Obviously, you might get a negative sign, right? This just says that the volume of something is 13. Well, the volume of what? Well, the volume of this little box I'm going to create. Imagine we're in 3 dimensions, so that's going to take 3 axes. We've got an x-axis, a y-axis, and a z-axis, and starting at some point, suppose we look at this vector, it tells us to go 3 in the x direction, 1 in the y direction, and none in the z direction. So we come forward 3 out this way and over 1, and that gives me a little arrow from my starting point. Say my little arrow from my origin, if you like. Okay, now here's another vector or arrow, and this one says I'm supposed to go, let's draw the negative x and negative y axes in here. This one says you go back 1 in the x direction, forward 4 in the y direction, and up 1, 2. So we get an arrow like this. Now those 2 arrows, if I copy this one and put it on the head of this other one, and I copy this vector 3, 1, 0, then it's going to create a parallelogram, right? So then I'm going to take this third vector, 2, 5, 1, that says come forward 2, out 5, so far we'd be here, right? And then climb up 1. Okay, and that makes the third vector. If I take that vector and I copy it to all 4 corners of my parallelogram, see how I made 4 copies of that same vector? Connect up those with copies of the vector from the ones above, I have a little box. Only since these corners aren't right angles, it's not actually a rectangular box. It's made out of parallelograms. We call it a parallelepiped. Parallelepiped. Some people say parallelepiped. I can't even spell it, so I'm not really picky about how you say it. Okay, so we've got this parallelepiped. Turns out the volume of that parallelepiped, the volume inside that box, is up to a plus or minus sign, the determinant. So I'll just ignore the negative sign. I know the volume of that box is 13. That's going to be pretty handy later on. Now determinants have many more applications than that, so they're a pretty cool computation in and of themselves, but it's kind of interesting that a determinant of a 3 by 3 matrix measures the volume of some sort of box.